Hello, everyone. Well, we are going to try to move up in the world. This time, I have in front of me the notes, so you should download those notes and have those handy. I also have my PowerPoint printed, so maybe I can go a little bit back and forth between the PowerPoint to share the pictures with you and the notes page to help you based on your feedback. And I also printed out my homework because we're going to end by doing a couple of example problems on the homework sheet. So I think you're going to want to have both of these in front of you, especially if you're printing your work. Secondly, we're going to need a calculator today, so make sure that is out and handy. And I don't know how long the video is going to take, so I may have to stop it part way and move to a part 2, but we'll kind of make the decision as we go. All right, I'm going to start by looking at my slides here. So let me just move this. And we are on a topic today, or starting a topic today that's called electrostatics. But let me give you a better sense of really where we are. So these are the 5 main topic areas in physics. So mechanics was everything from when we did kinematics and the motion graphs, all the way until we did dynamics, then we did work, power, energy, we did momentum, we did oscillations. So mechanics was a really, really big topic. Then we went into heat and thermodynamics. And so we've spent the last, I think, 3 weeks on heat and thermodynamics. And the first law of thermodynamics actually connected these two topics together. So that's going to be kind of important for us to remember as we go further here. So starting today, we are now going to be on the third main topic area, which is called electricity and magnetism. And under electricity and magnetism is the topic of electrostatics, the topic of circuits, and the topic of magnetism. I'll be honest, I think in all of the topics in physics, this might be the most difficult topic. And I only say it's difficult because it's things that we really don't see in our everyday world, because everything we're going to be talking about is invisible, super, super small at the size of an electron. And they might be things that in your everyday world, we just really don't talk about sometimes. When we get down to waves, light, and sound, even though it's invisible, we have a better comprehension of those topics. So that's a reason sometimes people get a little bit anxious with this topic and they feel a little bit confused in the beginning, but it's also a reason why I really like this topic, because it introduces you to something that you've maybe never thought about. All right. Anyways, this topic that you and I are doing is electrostatics. All right. So we're doing electrostatics, which is the study of charges at rest. And then circuits is when those charges start to move. And then once you have the charges moving, what other things happen? And I'll just give you a little tidbit on magnetism. We're not going to spend a lot of time on magnetism, but one of the things that happens with moving charges is we get a magnetic field around our Earth, and the northern lights, the northern and southern borealis, are all the effects of moving charged particles in our atmosphere. So again, things that are invisible that we maybe really didn't know about. All right, we are going to be talking about, we're going to introduce charged particles in this assignment, and we're going to also learn about the electric force and Coulomb's law. And then in the next lesson will be electric field, electric potential, and the concept of work. And then that would be it for electrostatics. So there's going to be 2 main assignments that go along with this. All right, the next thing. There are 4 conservation laws in physics: and conservation of mass, conservation of energy, conservation of momentum, and today is the last conservation law, conservation of charge. Quite simply, it says that charge cannot be created or destroyed. But said another way, when the Earth was born, we were given so many protons and so many electrons. And the number of protons will never ever change. The number of electrons will never ever change. And they can be rearranged. And you talked a lot about the rearrangement of things in chemistry. So that leads us to, in physics, we have been so far talking about masses. And when we have a mass, there's an assumption, like here's an example of a mass, but now instead of the word mass, I'm going to call it a particle, because for the most part, we're talking about small, small things. So this particle, all of the masses that we've talked about so far have been neutral. And if they were neutral, it means that they had an even number of protons and electrons inside the particle. We're not even going to talk about the neutrons because they don't come into play. So my example here has 7 protons and 7 electrons. If you want something to become negatively charged, if I want a mass or an object to become negatively charged, I have to give it some extra electrons. If I want something to be positively charged, I don't give it positive charges. I can't give it positive charges. Positive charges can never ever move because they're locked inside the nucleus. But I could take away some of its electrons, and if I took away some of its electrons, then it could become positively charged. So on your notes here, I ask you, what would you have to do to make this neutral particle have a -3 charge? So quite simply, I'm going to have to add, I'm going to write it in my sheet here, I'm going to have to add 3 electrons to it. So we haven't talked about how we're going to do that, but that's what I would need to do. And then if I did that, I'd have 3 extra negative charges, and then we could say that this has a charge of -3. How would we create a positive 3 charge? We would have to remove 3 electrons. If we took 3 electrons away, then it's going to have a positive 3 charge. So how do we take electrons away or add new ones? So in physics, we talk about electron transfer. And it says electrons are most easily transferred by friction or by rubbing. So here's an example. I have a plastic pen. Let me put my lid on. All right, here's my plastic pen. And if I was in class, I have a piece of rabbit fur, like real rabbit fur. And a rabbit fur works really well, but I don't have that. But I do have my fleece jacket here. And so you just rub, rub, rub like this. Rub, rub, rub. And when you rub, you transfer electrons. So some materials give up electrons more readily than others. Here's my example of rub, rub, rubbing with a rubber rod and fur. So I could do this one in class. But it says, what will happen when a glass rod is rubbed with a piece of plastic wrap? You know what? I put that in there because I meant to go grab a glass rod and a piece of plastic wrap that I did not do. So we'll pretend I rubbed the rod with a piece of plastic wrap. And so my question is, what became negative and what became positive? So you usually need a chart like this. And you wouldn't know unless someone gave you a chart. But if I had a glass rod and a piece of plastic wrap and I rub them together, it says here that glass has a higher tendency to lose electrons. And plastic wrap is down here, has a tendency to gain electrons. So I'm guessing that some of the electrons went away from the glass. That would make the glass turn positive. And the electrons, when they go away, they have to go somewhere. They went to the plastic wrap, and then my plastic wrap became negative. So far in our topic of mechanics, everything has been neutral. And now in the start of this third major content area, we have to start transferring electrons. And so sometimes electrons are going to get transferred to something, and then it now becomes a negatively charged particle. And it's a negatively charged mass, a negatively charged object, negatively charged particle. We are just going to generically say a charge. So now we would have a negative charge, and now we just made something that has a positive charge. And in our atmosphere, like way, way in deep space, There's lots of collisions taking place between atoms, and electrons are constantly being transferred. And so we have lots of charged particles naturally in our world. I also put this example here is when you walk with your shoes on carpeting, scuff, 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 and you know that you pick up electrons, you pick them up from the carpet, and you know that because you're able to shock people sometimes. And but when you wear your tennis shoes are pretty insulating, and you don't pick up as many negative charges with tennis shoes as you do with other types of shoes. But anyways, how to predict what's going to turn positive or negative, use this chart here. Okay, the next thing on number 8, it says an electroscope is an instrument that can be used to detect electrostatic charge. So this is nothing more than a flask from chemistry. This is just like a metal pole that's got this little metal ball on top. And we're just going to pretend now that my pen has become negative. So I rubbed it on something, and my pen is now negative. And then if I took my pen, I forgot to talk about these. These little guys down here are called leaves. They're really little pieces of like aluminum foil. But like real aluminum foil is kind of like too thick. But do you ever notice that inside like bubble gum wrapper, if you open up the bubble gum wrapper, sometimes there's a little teeny thin piece of foil in bubble gum? So if you take that little foil out and you hung one of the pieces here and one of the pieces here, so it's like really, really thin metal. And I know that because when these things rip and I have to get new ones, I don't go order them from the science company. I get them out of bubble gum. Okay, so I now take my rod, which is negative, and I touch the ball. And so all of those electrons, those extra electrons in my pen, then go into the ball. Electrons like to spread out, and they go into the ball, and they go down here, and they go onto these little metal leaves, and the little metal leaves become negative. And then because they're so light, they have the ability to repel, because we know that like charges repel. And honestly, this is a little bit more confusing, but if my pen was positive, here's another example of an electroscope. You can make a simple electroscope by just taking two balloons, balloon, balloon, and this is just a piece of string. And you can do the same thing by taking my pen. I'll go back and pretend it's negative for a minute. And so if I pretend it's negative, now the negative goes down into the string. String doesn't transfer electrons as well as the metal here. And my balloon can become negative. It actually becomes negative on all sides, but you can see then my balloon would repel each other over here. But I also want to make it clear that if my pen was positive, and then I touch this, now, since my pen is positive, lots of negatives, now lots of electrons come out of the flask and the rod, and they go into my pen because they're attracted to my positive pen. That would leave this system here positively charged, and these little leaves become positively charged, and they still repel because two positive charges are going to repel also. So just by seeing the leaves repel, I don't always know if it's positive repulsion or negative repulsion, but I did prove that my pen must have been charged. So that's what electroscopes can do. So we should be familiar with that. Okay, so moving on to some more details. All right, we're now talking about a charged particle. If we were talking about a mass, we used to use lowercase m. And sometimes if we were talking about a really, really big mass, like the mass of the Earth, we would use capital M. But now we have transferred electrons so that we have a charged particle or a charge. And so my charge, if it's a really big charge, sometimes we use capital Q. And if it's a smaller charge, we might use a lowercase q. But the point is the variable for a charge is Q. And yes, the variable for heat was also Q, but that has nothing to do with this. Okay, the Q's are totally, totally different. The unit of charge is named after Mr. Coulomb, just like we named the unit of force after Mr. Newton. All right, but charges are a little bit different than masses because charges can be positive or negative. So I can have plus Q's or minus Q's, or I could write it as plus Q's or minus Q's. All right, what is the very smallest negative Q, negative charge that I could ever pick up in the universe? That would be an electron. That is the smallest negative charge that exists, and the smallest positive charge is a proton. So the smallest charge is Q. If it's an electron, we're going to put a negative in front of it. If it's a proton, we're going to put the positive in front of it. So if the unit of charge is a coulomb, what is the value of this charge? And the value of one electron, it has a Q value. It's got to be a negative value of 1.6 times 10 to the minus 19 coulombs. That's tiny. That's the smallest charge that we can have, the smallest negative charge. And electrons and protons have different masses, but they don't have different charges. They have the identical charge, 1.6 times 10 to the negative 19. The electron one is just negative and the proton one is positive. So I would tell you that this is a number that you'd have to memorize. If we were going to be in this unit for a really, really, really long time, you got to know this number. But we're not going to be in the unit really long, so you might start to memorize it, or you might have to come back and look it up. But this is a number that we need to be aware of. All right, so you can see that an electron has a very small Q value. So then the question becomes is, what if I actually had a full coulomb, like a full 1 coulomb? Like how big is a charge of 1 coulomb? A charge of 1 coulomb is really, really, really big. So it's very, very large, very, very dangerous. I think I put in your notes that a lightning bolt is between 3 to 90 coulombs. Like 3 coulombs is a lightning bolt. So we're not going to get answers of coulombs. We're going to get answers that are like really, really small coulombs. In fact, 1 coulomb is equal to the charge of this many electrons. So 6.25 times 10 to the 8, you'd have a lot of electrons or protons in a pile to come up with a charge of 1 coulomb. All right, I'm going to go a little bit further before we call this video done. All right, the last thing that we need to know then is that charge is quantized. And quantized means that charge can only be transferred in whole number multiples of electrons. You cannot transfer half an electron. So I'm going to jump down to the bottom here for a minute. It says all values of charge have to be multiples of 1.6 times 10 to the negative 19. If the smallest thing that I can pick up is 1 electron, that would be its charge. But what if an object had 2 electrons? Then this would be its charge, 2 times that, and its Q value would then be negative 3.2 times 10 to the negative 19 coulombs. What if an object had 200 extra electrons? Then its charge would be 200 times that many coulombs. And if we lose electrons, then it becomes positively charged, and everything is a multiplier of this. That's what the word quantized means. It only exists in these certain lumps. And in real life, something else that is quantized is money. Money, the smallest piece that you can have is 1 cent. You can't give somebody 1.5 cents. You either get 1 cent or you get 2 cents. And that's the same thing with charges. Every single charge is some sort of multiplier of this number. All right, so that's the basic foundation here. So I'm going to stop this video and then we're going to go back. We're going to go more into the details and the number crunching and the equations that go along with this idea.